Hello, everyone. Can you hear me well?
Hello, Priscilla. I can hear you.
Hello, Ricky.
Hello.
Hello, everyone. Thank you very much for attending our event. We are here with this technical presentation about rock mechanics applied to the oil industry. This is an activity promoted by our AAPG Young Professional chapter. Is a chapter formed by professionals or students in postgraduate students in partnership with the Young Professional Mexico chapter. Our main role is promote activities, networking, technical capacitation to our young professionals in our industry. So, as you know, AAPG promotes a lot of activities involving not just companies, but also involved institution, geology institution, research, universities, and so on. So, our main objective through this young professional chapter is promote this kind of capacitation. So I will invite you, I would like to invite you to send this link on YouTube to your friends and to your student chapters and to your partners and companies and promote the geoscience through the AAPG activities. So first of all, I'd like to thank you, the IP chapter from Mexico, here represented by my dear friend Enrique Cedas. So please, Enrique, if you can say some words and present your chapter, will be perfect. The floor is yours.
Thank you, Priscilla. Thank you. We are so happy to be with all of you guys. We are pleased to be invited to this event. It have not been the first time we have worked together as YPs from different countries. And as Priscilla said, we are also compromised and we are encouraging these YPs, the young professional from both sides, to give them some knowledge, some new perspective, some tools, some different areas to be more prepared in their day-to-day. So I'm gonna share my screen just to show for the people who doesn't know us what we do. I'm sharing my screen. Okay. Well, for the people that they have not heard about us, as part of the AAPG, the American Association of Petroleum Geologists, the Mexico chapter. The Mexico chapter is built by different young professionals from different institutes across the Mexico, the geoscience fields, and we have had different backgrounds from petroleum engineers, not just geologists, also geophysicists, industrial engineers. So we are trying to open the fields to not just to geologists, and we are focused, as Priscilla said, to the sharing of knowledge with different, and we had in the past different activities like conference, symposiums, round tables, and some social activities to integrate all the members and others they are getting in. And we are now in the online era, so we are making online sessions that we all invite you to follow us, to join us as well. If you are from Mexico, to contact us. We are going to share our social medias. We are going to have the ready to work as well as YP Brazil, I think they're having now, they're going to have. So be in touch, stay tuned for next activities of both chapters, and we invite you, we need hands to do this, all activities to achieve the goals, to go with the all YPs across Mexico. So please, if you are interested to join us to the YP Mexico chapter, please send us an email, our Facebook or LinkedIn message, and we are going to be very happy to answer you. So thank you, and we are happy to as well to be here with you.
Thank you very much, Enrique. As Enrique said, AAPG have a lot of activities focusing in developing our skills and technical skills of the young professionals. So we have many activities and opportunities to not just the young professionals, but also to the new students. Actually, recently, Brazil, throwing a student chapter, win the first place in the competition Imperial Barrel Award. So this is a huge achievement for the Latin American region. So this is the result of many efforts together with companies, with universities, with professionals who are engaging to promote this kind of capacitation and this kind of activity to increase our technical or soft skills or whatever we need to give to the industry what they need, right? So if you are Mexican or if you are Brazilian and you are a young professional until 10 years of experience and you never heard about AAPG, please send us a message by LinkedIn, by the contacts here in the chat. So we will please to give you all the information we can and all the opportunities that you can give through this association, this global association. So please send message to Enrique or me, and we will. Happy to. Are you hearing me?
Yes, we can hear you. You were freeze a moment.
Okay, I think it's my bad connection, the internet connection. Sorry.
Now we can hear you.
Okay, so let's get started to present our speaker for today. Okay. Our speaker will provide us a technical presentation about rock mechanics applied to the oil industry. And this speaker is Geraldine Pedrero. She is a geologist engineer from Universidad Autónoma de Nuevo León with 10 years of experience in oil and gas industry. Began her career as a modelogger in onshore fields of Mexico. Later in 2012, she moved to Weatherford Laboratories, now Stratum Reservoir Laboratories, where she have been leading the rock mechanics laboratory, analyzing mechanical behavior of the rock through lab testing, like triaxial test, USC, acoustic velocity, smoke, column bore analysis, think wall, cylinder, Brunel hardness, and Brazilian test, among others. So welcome, Geraldine, and thank you very much for accepting our invitation. We are so pleased for having you here, sharing your knowledge and your technical knowledge with us. I believe as you are geologist and engineer, and also engineer, you can share a lot of knowledge with us and show to Brazilian young professionals and to the Mexican young professionals what they can work with this role. Okay, so Geraldine, thank you very much. The floor is yours.
Thank you very much, Priscilla. Thanks, AAPG Young Professionals, for the opportunity to be here today to share with you about rock mechanics and how you can apply these tools in the oil and gas industry. Let me share my screen now. Okay. Okay. Good. Well, just okay. Let's start. Okay, well, thanks again. Thanks for all the people who is attending this presentation today. As Priscilla said, I have been working all these 8 past years in rock mechanics laboratory. So it's a pleasure for me to share with you the knowledge I have been acquiring along these years. So our agenda today will be a brief introduction about basic concepts about the topic in rock mechanics. Then I would like to show you an equipment used in rock mechanics and also the material we use for this kind of test, the quality controls that every rock mechanics laboratory should have, then enter to these tools of rock mechanics that you have available in the industry in order to optimize your exploration and production activities. So at the end, I will share with you a testing matrix that will help you to decide what kind of tests are better for you in any kind of situations. Well, I would like to start with 2 concepts. I would like to define the difference between geomechanics and rock mechanics. The geomechanics is the theoretical and applied science that study the mechanical behavior of all geological material. This includes soils and rocks. Then the rock mechanics is part of the geomechanics, but is focused in a laboratory level in a rock sample and offer a direct measurement of the rock to analyze the deformation and a possible failure of the rock in consequence or by consequence of the change in pressure, temperature, or stresses. This pressure change or temperature change results from the geological evolution in the time, but also from the oil and gas exploration and production activities like drilling, hydraulic fracture, water or gas flooding, etc. So, as I say, geomechanics study soils and rock, but in the petroleum industry, the geomechanics tends to focus on rocks. Say that I also would like to define another term that is petroleum geomechanics. The petroleum geomechanics will be the discipline that integrate rock mechanics, geophysics, petrophysics, and geology in order to quantify the air change caused by this stress, pressure, and temperature changes in the time. Well, the objective of this geomechanics is to predict when and where the failure will occur in order to assess the risk, study opportunities, and propose mitigation plans. With that, we can reduce non-productive times, reduce costs, and reduce risks. But how and where can we apply the geomechanics? Well, in a development phase, the geomechanics can help you to determine the better or the best trajectories for drilling, to define the casing points. Also, and very used is for define the mud weight. In geology, can help you to predict the permeability for anisotropy fracture reservoirs. And in production phase, it will help you to select the optimal completion methodologies to predict when you are in the production first phase or depletion. It will help you to predict any change in your reservoir performance, assess techniques for repeated hydraulic fracture, and indirect recovery, secondary and tertiary recovery, optimize your process such as water flooding and gas injection. So where does geomechanics impact? As you can see, geomechanics impact is from well to field, from exploration to production to abandonment. As you can see in this diagram, there are many problems that can be mitigated if you apply geomechanics, if you do this through a good geomechanical characterization. In order to build a good geomechanical model, geomechanical specialists need to integrate a lot of information. And part of this information is rock mechanics properties or mechanical properties of the rock. So some of these parameters are UCS, friction angle, cohesion, Young's modulus, Poisson ratio, and the thick wall cylinder strength. You have two sources in order to get these parameters. This will be petrophysical logs or well logs, and also, of course, rock mechanics testing. It's important to me to mention that rock mechanics tests are a very important parameter in order to calibrate the petrophysical logs. Have been proven that there are not any technique that can measure your rock strength in situ. So the only way you can measure directly is by a rock in a laboratory testing. So that's the reason every geomechanical specialist should also ask for rock mechanic testing in order to calibrate their logs. Okay, before I will start talking you about rock mechanic testing, I would like to define some concepts that are mostly used in rock mechanics. I will start with overburden stress. What is the overburden stress? This is not more that the column, the rock, the weight of the rock that is overlying your formation in a given depth. All that way that is overlying the point you want to study is the overburden stress. It's also called lithostatic pressure or vertical stress. The pore pressure, well, the pore pressure is the fluid inside the pores of the rock that are also overlying the point you want to study or the depth, the given depth. It's also called reservoir pressure. When you have unconventional rocks like shales that have very low permeability and they suffer compaction, that water inside or fluid, inside the pores of the rock cannot migrate or escape because of the low permeability. So in that case, this pore pressure it comes higher in and is when you have zones with abnormal pressures. The other one is the confining pressure. The confining pressure is the combination of the hydrostatic and lithostatic stresses that you will have around your rock or formation. In the laboratories, the confining pressure will be the load or pressure that you will apply around the sample or the radial load. Young's modulus. The Young's modulus, also known like elastic modulus, is represented by the letter E. And this property can be just defined like the stiffness of the rock. In other words, it's how easily your sample or your rock will bend or stretch. The measurement of Young's modulus is based in the relation between the axial stress and the axial strain of the rock or the sample. Poisson ratio is a phenomena where the material or your sample tends to expand in a perpendicular direction to the direction you apply the stress. In this case, in rock mechanics, you normally apply a vertical stress, and the sample tends to expand in a perpendicular way. Well, now I would like to show you a triaxial cell. This is equipment for rock mechanics. There are many models of this kind of equipment, but today I will show you the one I have in my laboratory, well, a strong laboratory. This is a rapid triaxial rock testing system. It has capability to apply axial load of 1,000 kilonewtons and up to 20,000 psi of confining pressure, and also it has capability to apply up to 200 Celsius degrees of temperature. All triaxial cells have platens. These platens that you can see right now in your, let me activate, okay. That you can see right now in the screen will help you to support your sample. You can find platens for 1 inch, 1.5 inch diameters, 2 inches, and also some laboratories has platens for full diameter samples. Then another component for a triaxial cell are the sensors. These ones here are called LVDTs, are axial LVDTs, and will be placed in both sides of the sample in order to measure the axial strain or axial deformation. And then you also have a radial LVDT. This is placed around the sample and is to measure the radial strain. As you can see here, this is my sample. Our samples are cylindrical, are called blocks. Normally, you put the sample inside a sleeve. This is to protect the sample to the oil that will be applied around the sample in order to apply a confining pressure. Then this picture is just like how looks the sample already assembled. Here you can see the bottom platen, top platen, the LVDTs in both sides, and the radial LVDT around the sample. Then this assembly is put below the cell. The cell is lower and filled with oil. Well, this is in case you will do a triaxial test. If you will do a UCS, it's not necessary to fill with oil. And the last one is, this is an equipment. This is an oscilloscope, is to measure the acoustic velocities, is plugged to the equipment, to the platens. And with this equipment, you can measure acoustic velocity, the arrival time of P wave and S wave. Also, there are many kinds of equipments in order to do this service or this test, but the most used equipment are oscilloscopes. Okay, as I told you, I would like to share with you some quality controls that I consider every rock mechanics laboratory should have or take in account. The first one, I think the most important, is the sample homogeneity. When you will do a rock mechanics test, you want an homogeneous sample. Why? Because if you have a sample that have part of one lithology and the other part of another lithology, you are not measuring any of both of those lithologies. So you always want an homogeneous sample representative for one lithology or fascia. So how can you do this? Well, at the beginning that you have your entire core, you can do a visual inspection, see or identify all your fascias or lithologies in the core, and select the more homogeneous points in the core, and there's where you will do the plugging or sampling. Once you have your plugs or samples, another very helpful tool is the CT scanning. With the CT scanning, you will be able to see the inside of your sample, the internal structure. In that way, you can see if you have a grain, a very big grain inside, an internal fracture, any heterogeneity that could affect your results or influence in a bad way your testing. In that case, you decide to not run that sample. Okay, the second one is the sample cooling. You want to cool your sample in order to preserve the natural moisture of the sample. In rock mechanics, when you run a test, you want to have the sample the more close of the reservoir conditions. For that reason, when the sample or core arrives to the laboratory, it's very important that rock mechanics plugs are taken first. And then when you have the rock mechanic plugs, you want to refrigerate these plugs in order to preserve that natural fluid content until you will run the test. Okay, another quality control is dummy tests or dummy samples, we call that way, and is when before you start a new project, you want to check or review that your equipment is working fine in all ways. Sensors, piston, confining pressure, all the wires, etc. So in that case, what you do is to run a dummy sample of a rock that you already know the parameters or the results. doing this, you make sure that everything is working okay and you won't have problems with the real samples. Okay. The other one that you should apply is the annual, well, the maintenance of the equipment. In this case, we do this annually with the manufacturer of our equipment. And the last one is a recommendation. In our case, every time we will start a project for a new reservoir that we never studied before, we receive a feedback between the specialist in the lab, in this case myself and my partner, and the subject matter expert or technical advisor for rock mechanics that we have in our company. In this case, he is located in Colorado. Okay. Say that, now I will enter to the laboratory testing that are available in rock mechanics. So I would like to start with compressive strength test. All of them share some characteristics or conditions. I will start with sample dimensions. Talking about sample dimensions, by recommendations of the International Society of Rock Mechanics, you should have, or the optimal relation between length diameter should be 2:1. The minimum recommended is 1.41 in order to avoid the influence of friction and effects in the results of your testing. So this means that if I have a 1-inch diameter sample, the optimal length will be 2 inches, but the minimum could be 1.4. For 1.5-inch diameter samples, the optimal length will be 3 inches, but the minimum accepted is 2.1-inch diameter. Length, sorry. Okay, now then the samples conditions for compressive strength test, you normally want vertical plugs. What this means, that when you have your core, you identify the bedding, and normally you do the plugin or sampling in vertical way, or you identify the orientation of the bedding and you want a plug that is perpendicular oriented to the bedding. Then again, homogeneous samples and representative samples from every lithological fascia identified in your core. The strain rate. The strain rate as a standard, we use 5 × 10 to the -6 strain per second, but optional in case or for unconventional reservoirs where you have very, very low permeability, you can also use these other strain rates. What about saturation and pore pressure of the sample? Well, normally, by standard, samples are running as received. What this means, we don't saturate the sample with any fluid because, as I say, we keep this in refrigeration until the testing moment in order to keep the natural fluid saturation. So, but optional, if the client required or the people who is requesting the test do this requirement, it can also be saturated with a solution of KCl at 7%, or even with any brine that they require, and we can create it in the laboratory. So pore pressure as a standard also, the sample is run at effective stress. This means no pore pressure, but optional, if they require, you can run the sample pressurized with any pore fluid, or as I say, with KCl at 7%. Confining pressure. Well, I already told you what is the confining pressure. So the confining pressure will be determined with the data provided by the client. This is very important. The client have to provide you pore pressure, overburden, and Poisson ratio. So if the client don't provide you with this information, you can also do an estimate or calculation of this confining pressure using the following parameters. For overburden, you can use a gradient of 1.084 psi per feet. This is based on the presumption that you have an average overburden density of the rock of 2.5 grams per cc. So for pore pressure, you can use a gradient of 0.434 psi per feet, based in the presumption that you have a density of the fluid overlying of 1 gram per cc. This is taking in account a normal pressure situation. And commonly, the Poisson ratio is taken as 0.25. This Poisson ratio is a dimensional value. So then how you will calculate the confining pressure? First, you want to determine your horizontal stress with this formula. We use horizontal stress minimum and maximum at the same, presuming that you have an isotropic material or homogeneous material. Then when you already calculate the horizontal stress, you want to calculate the effective mean stress, and this is the value that you use as confining pressure in rock mechanics testing. Okay. Well, now the first compressive strength test is UCS. It's the most common one. The goal of this test is to determine the compressive strength of the rock and the static elastic parameters of the sample tested. It consists in to apply an axial load to the sample until the sample fails. With this test, you can get the total peak of axial stress when the sample fails, the static Young's modulus, static Poisson ratio, and optional, you can run acoustic velocity in conjunction with this test. The second one is a triaxial compressive strength test. It's similar than the UCS. It's the same goal in order to get the compressive strength and also the static elastic parameters, but this time applying a confining pressure around the sample. It consists in the same. Apply an axial load to the sample, but this time the sample is under confining pressure and you will get the same data. How it looks, the deliverables? Okay, the deliverables looks like this. You receive a chart with your samples depth. Sometimes we give the rock type, the confining pressure. In this case, for this example is for UCS. It means unconfined compressive strength test, no confining pressure applied. Then you have the total peaks of compressive strength, the Young's modulus, and the Poisson ratio. This is the representation, this graphic, the representation of the test. Here, the blue one line is the axial strain, and the red one, the radial strain. Also, you receive a plot that represents the Young's modulus and one representing the Poisson ratio. If your project have many samples, we also have, we compile all of these in a blog where you can see the performance of each of these samples. Then also a graphic where you can see all the samples tested in this plot. This is the depth versus the compressive strength. What means these colors or the difference? In this case, for this project, it represents the difference of lithology. You can see in the chart before, the three first samples were sandstones and the other ones were clayey siltstones. So the color is just to differentiate the lithology. These kind of plots, this one is depth versus Poisson ratio, and this is depth versus Young's modulus, will help you to see if there is a tendency in the parameter. In this case, you can see at more depth, the sample increase their total peak strength or their strength. Another test is the Moore-Coulomb analysis. Well, this is more like analysis. There are two methods in order to get this. One that we call RM-Pro, and also the multi-stage, very used in the industry. The goal of both of these methodologies is to determine the compressive strength of the rock, also the static elastic parameters, in order to have all the data necessary to build a Moore-Coulomb failure envelope. What are the difference between these two analyses? Okay, well, the RM-Pro is a suite of tests that requires 3 or 4 samples at the same depth. We call these twin samples. You want your samples be on the same depth or very close in the same lithology or fascia. Then you run every of these blocks. These are your twin blocks. You run these blocks in different confining pressures. Normally, if you have the 4 blocks, you run a UCS. It means one block with no confining pressure, a UCS, and the other one triaxial test at different confining pressures. Doing that, you get all the data to build the Moore-Coulomb envelope. In the case you don't have enough sample, you just have one block, and then you can also do a Moore-Coulomb analysis, but this time you will use the multi-stage method. In this method, the block will be taken to a first confining pressure, and then before it breaks or fail, you will take out this confining pressure. You will take out the load, the axial load, and take the sample to the following confining pressure and start applying axial load again. And before it fails, again, you stop, retire the axial load, and take the sample again to the next confining pressure. You can do this with 4 stages or 5 stages. With that, also you will get all the data necessary in order to get to build a Moore-Coulomb envelope. The deliverables for this kind of test is like a UCS and triaxial test, the total peak of axial stress, the static Young's modulus, static Poisson ratio, the Moore-Coulomb failure envelope that include the coefficient of intact friction, the friction angle, the cohesion, and the graphics of the curriculum envelope. The deliverables looks like this. You have, in this case, this is an RM Pro. You have all your samples here identified, the depth, that should be the same. As I said, this will be, or the optimal is that the samples be close enough or the same depth. The different confining pressures you use, and the results will be the slope. This is the slope. You get this in this graphic where you plot the confining pressure versus the compressive trend where the samples fail. You will get the friction angle, the coefficient of friction, and the cohesion. Then we have the ultrasonic velocity. This is another test that can be run in conjunction with any compressive trend test. The goal of this test is to provide a measurement of the P and S wave velocity in a rock sample. With this, you will get the dynamic elastic moduli. As I say, it can be run in conjunction with any compressive trend test. The deliverables will be the P wave velocity under hydrostatic conditions. It means when you apply the confining pressure, and it also can be measuring when you apply axial load, but normally the deliverable is just under hydrostatic conditions. The other deliverable is the S-wave velocity, the dynamic Jones modulus, dynamic Poisson ratio, dynamic shears modulus, and dynamic Boolk's modulus. The deliverables looks like this. This is a table with all the ultrasonic velocities, compressional wave, shear wave, and the moduli, Young's modulus, Poisson ratio, Boolk's modulus, and shear modulus. All of them dynamic, of course. And this is just a plot of how it looks. This is from P wave, and you can see here how we identify the arrival time. Okay, then another test is the Brazilian test, and the conditions for this test are by default or standard. You want POC samples, POC-shaped samples is like a disc of sample or a cookie of sample, trimmed from horizontal plugs. That means that you have an horizontal plug that was sampled from the core in horizontal oriented direction, and from that plug you trim a disc, and this will be loading in a perpendicular plane of the bedding. I will show you in the next slide a picture of that. For this test, we suggest to do this in 1.5-inch diameter samples. Why? The bigger your sample, the less you will have influence of any heterogeneity in your results. It means if you have any heterogeneity, little fracture on the sample grain, it will affect less if you have more area of sample. Sample saturation, it's the same as compressive trend. Normally are run as receive with no saturation, but if you decide to do this with saturation, the standard is KCl at 7% or any brine created in the laboratory. The strain rate of this test, the default or standard is 0.006 0.060 inches per hour. How we do determine this? You want your sample fail in a short time, more or less 15 minutes. So this strain rate was determined in the intent the samples fails in this time. Okay. This Brazilian test is also known as indirect tensile strength. The goal is to determine the indirect tensile strength of the rock. There are not any equipment that can take, or is very difficult to build an equipment that can take the sample or the rock in both sides in order to apply a tension. So that's the reason the equipments of rock mechanics are built in the way that they apply an indirect tensile in the rock. So as you can see here in the image, you place the disc of sample in order you apply your axial load perpendicular to the bedding, if you can see the bedding here in the sample. In that way, when you apply your axial load, you are causing a indirect tensile strength in the rock. So, with this test, we can correlate the UCS value. This is some benefits or advantage of this test. It's easy to prepare the sample. It's easy to get the samples because you don't need a lot of rock. It's fast and cheap. And what is the usefulness of this test? For hydraulic fracturing, you need to overcome this parameter, the tensile strength of the rock. So if you want to have a better understanding of what to expect in a fracking operation, this test is a recommendation. So the deliverable will be the Brazilian indirect tensile strength of your rock. The deliverable looks like this. It's just a table with all the sample information, the maximum load where your sample fails, and the Brazilian tensile strain measurement or calculation. And this is the plot that represents the test performance. Okay, then we have feedball cylinder. For this test, you want samples for 1.5 inch diameter. We use here the same length diameter ratio of 2:1. So the optimal will be 3 inches of length, but the minimum could be 2.1 inch length. So in this block, you will drill a hole, a central hole of 1.5 inch diameter, and the measurements are conducted also in vertical oriented samples. The saturation is the same as received or a standard with KCl or any brine solution. The confining pressure loading rate will be, as a standard, 100 psi per minute. In this test, you want we also want to fail the sample in a short time, in an appropriate time. That's the way this loading rate was determined by recommendation of International Society of Rock Mechanics. The goal is to provide measurements of the collapse strength of a cylinder with a hole in the center in order to predict sand production. This is the main usefulness of this test. And the deliverable is the confining pressure when the sample fails or collapses. It looks like this. The plot of the test performance. Here is the point where the sample collapsed, or the hole in the center of the sample collapsed, and the data of the sample, and the confining pressure is here where the sample fails. Okay, another test of rock mechanics available in the industry is the uniaxial per volume compressibility, also known as UPVC. The goal of this test is to measure the elastic response that elastic answer that a samples have in one direction when it's taken to reservoir conditions and you increase the overburden pressure, increasing your axial load as a result of the depletion. In this test, you represent the depletion or the production of a reservoir. What is the usefulness of this test? Well, this helps the client to determine the reservoir compaction during the production phase or depletion phase. And the deliverables will be the per volume compressibility, of course, and optional grain compressibility, the drained bulk modulus at constant pore pressure, drained bulk modulus at constant confining pressure, and Biot coefficient of the rock. Propan embedment is another test. The sample description that you want for this test is a sample of 1 inch diameter per 0.4 inches of length. This means you also need a little bit sample. It's like a cookie or a disc of 1 inch diameter. This is you get this sample from an horizontal plug. Again, you trim this into this plug, and you get all the necessary pieces that you need in order to get all your project done. Saturation. Here, the sample, the standard is to saturate the sample with KCl at 7% for 30 or 45 minutes prior to the testing. Optional, we can create any brine at the laboratory. The strain rate will be 165 psi per minute. Why is this strain rate? Well, you want to apply a total axial strain, more or less, of 10,000 psi of axial load. And you want to reach that axial load in a time of 1 hour or 60 minutes. So if you use that strain rate, this is the time where you will reach that axial load. So the propan embedment is conducted in 2 parts. The first part is just a measurement of how your propan will compact. In this case, you use a propan embedment cell like this in the picture, and you just apply propan to the cell. You do all the tests, apply 10,000 psi of axial load in a time of 60 minutes, and then you analyze how your propan suffer the compactation or accommodate in the cell. So the second part, you will use the propan plus the rock. You will put first the rock, you will put the propan above the sample, and then repeat the same procedure. You apply at 10,000 psi of axial load, In this case, this is what you will do during the test. You have your sample, your propan, and that you want to get is how the propan indent in the sample. The main usefulness of this test is compare different kind of propans in order to define which is the better option for hydraulic fracturing. As you know, when you do a hydraulic fracturing, you will inject a propan, and this fracture will tend to close, and you want to evaluate how much the fracture will close after you inject the propan. So this is a very useful test in order to evaluate that. So you can evaluate different kind of propans in different kind of samples. Also, it is helpful to determine at what load your propan start to crash. Here in this plot, you can see the green line is the first part of the test when we just evaluate or test the propan and how this compact. And the second line, oh, sorry. The second line is the propan only. The red one is the propan plus the rock. And when you subtract the blue line to the red one, the green line is the propan indentation. Another test available in rock mechanics industry is the Brinell harness test. The goal is that to determine the Brinell hardness of the rock or the material. The test consists in use a carbide ball, normally of 10 millimeters of diameter as an indenter. And you will apply a loading force or axial load of 100 to 300 pounds. After you do this in the test, you will calculate the Brinell hardness through this formula. In this formula, you need the P represents the applied load. This means the 100 or 300 pounds. The diameter of the indenter, in this case, a 10 millimeter diameter ball, and the diameter of indentation. In this case, you can see here this image. You have to measure the diameter of the indentation your rock left on the sample or on the surface of the rock. And then you have all the data in order to calculate the Brinell hardness. Usefulness of this test is sometimes to build like a plot or log, because this is a very fast and cheap test. It can be done in many samples along the core. In that way, you can build this kind of plots and determine what are the better points or areas where you want to do expensive tests like triaxial or UCS or more Coulomb. So this will help you to evaluate the interesting areas for you. So we report to we do 3 indentations in the rock in every test, and we report the 2 most similar results. Well, this is the last test. I would like to close the presentation with this testing matrix that will help you to define what kind of test you need in every situation. For example, in this matrix, you can see all the test abbreviations. This and the second column, you can see the entire name of the test and all the parameters you can get from this test. Here, the recommendation of how much samples or tests you should run of each of these and the applications. For example, if you are looking to get just the static elastic parameters as Young's modulus, Poisson ratios, you can see here that all these tests will give you these parameters. But if you just want that, you with a UCS and triaxial test, you will get that. But for example, if you are looking for a more column envelope that give you also the cohesion and the coefficient of friction here, this you want to do a more column analysis, and you have two methods to do it. So if you are looking to do a hydraulic fracturing design, here you can see the applications. You can look, oh, I want to do a hydraulic fracture design. So you look here, and this one give you that you should do a Brazilian test. This is the indirect tensile strength test. So this is how you can define what you want to do and in what moment you need to do it. So I know this matrix has a very, very low size of the letters. So if you want me to share this with you, leave a comment and I can share this matrix with all of you. So thank you very much for your time. If you want to contact me, here is my email. And if you want to know more about our capabilities in rock mechanics or the other areas of the laboratory, please visit our social media.
Thank you very much, Geraldine, for your great presentation. Can you hear me?
Yes.
Okay. Thank you very much. I think was a very good presentation. So we have some questions. I think we have a few minutes to respond to these questions. Okay, Laura, if you can remove the presentation. No problem. Or if you want to back in a slide during the answers, Geraldine, please. It's up to you, okay? So, Geraldine, during your presentation, we received some questions. Luis Rafael, I don't know where he's from, but he wrote, the tests are only for core samples. Any experience with drilling cuttings?
For me, I don't have any experience with corings. That I know that yeah, rock mechanics can be done in corings also. It's not frequently to do this, but yeah, there are some tests. Actually, these are indentation tests that can be done on coring samples. But on my experience, I only work with core samples.
Yeah, I presume that because you will measure the mechanics properties of the samples, it's more easy to calculate in the course, right? So,
yes.
But I don't know. We do not know the whole technology that we can find.
Yeah,
So
it's more common to get a blog and study a blog that and more representative than corings. Yeah.
okay. So we're gonna to the other questions. Let me check. Okay. The other question is what parameters from petrophysics can be related with the rock mechanics? If possible, can use the petrophysical logs or just the petrophysics laboratory data?
in order to build or do a geomechanical characterization, of course, you will use petrophysics information. As I say, petroleum geomechanics use geology information, geophysics, petrophysics, and rock mechanics. You will use all this information if you want to do a really good geomechanical characterization. But of course, as I said, you can get any of these parameters, UCS, Poisson ratio, Young's modulus, through petrophysics logs. But a good practice, a very good practice, is that you also do laboratory testing, because this is a direct measure in the rock. It's not continuous like a log, but is directly in the rock, and you should do this in order to calibrate that petrophysics logs and make sure that you have a good data.
Okay, perfect. We have another question from Maria Jose Peña Teles. Thank you for the information that you shared with us. What do you use the key KCA, I think, as a standard for sample saturation?
Oh yes, yes. As I mentioned several times, that the standard, if the sample or the test is required with saturation, or to saturate the sample, as a standard we use KCl at 7%. Why? Or this is your question, I think, is because the KCl is a preparation with potassium that, in the case your sample or your rock has a content of clay, it won't swell that clay. It helps to avoid the clay swelling. That's the reason, that's the standard solution we use in rock mechanics to saturate the samples.
Okay. So unfortunately, our time it's up. It's ending. Geraldine, I'd like to thank you very much for your presentation. Your knowledge is more focused in the engineering part, I think, but you are geologist, right? So I think it's important to present for our audience that even they are geologists, they can qualify with others skills to provide the results that our industry needs and solving the challenges that our industry needs. So if you can send a message for these young people that they are starting their careers, and if they want to follow this kind of knowledge, what advice do you want to give them?
Yes, of course. As Priscilla said, I'm a geologist engineer. I'm not a mechanical engineer, but you don't need to be a mechanical engineer or any special bachelor degree or career in order to have your or specialize in rock mechanics, or work in this area. Um, Being a geologist engineer or mechanical engineer, petroleum engineer, give you the knowledge you need, or the basic knowledge you need in order to study rock mechanics or work with rock mechanics. Um, the advice that I can give you is that you really like to work with rocks. You are very interested in stresses, the formations of the rock. This will passionate to you. I really like what I do. I didn't decide to specialize in rock mechanics, but when I start working on this, I discovered this is like another world, and it's very, very interesting. There is a lot of knowledge that you will gain. Every day I learn more and more about this. And it's relatively a new discipline, but it's very important and very useful in the exploration and production industry.
Thank you, Geraldine, for your message, for your words. We have a couple of questions, but unfortunately our time it's ending. So Vivian and the other ones, maybe you can put the same questions in the comments of the YouTube channel. So after that, Geraldine can respond if you can, Geraldine, respond the questions in the comments. Okay. So thank you very much. Thank you for your time. It was a really great presentation, and I hope more professionals and more we can promote for our members more technical discussions and technical presentations. Okay. So have a great night. You stay safe, and cheers.